Cool. Thanks all for coming. I know we're kind of in the weekly quarters phase of the year, but there's a little less, in the rest of campus. Today we've got Jason Seawall from Numurus. Maybe some of you are familiar with him from his time at APL and his time at NEPI. But we're going to be hearing a lot more about AI. Go ahead.
And thanks everybody for coming. See everybody. A few faces out there. I guess just so I understand, how many engineers do we have here versus scientists? I guess let's see engineers first. All right. And scientists, we got a couple. And then everybody else somehow ended up here. Oh, that's great. I think some of you guys have run into and maybe attended one of my past presentations, but it's been a few years since I got down here, and so I'm really excited to show you where we're at. I think one of the things that we've done over the last 6 months is really put a lot of emphasis on delivering kind of near-term solutions for scientists and research, and so yeah. So I'm sure. Well, I guess how many people here are familiar with the term edge AI? And so it never hurts to kind of explain that, because people, there's AI, and then it's kind of like, well, if it's in the cloud, you can, that actually there's a massive amount of servers available to you. It's absolutely amazing what the kind of capabilities that are being created today. And whether it's robotics or any type of data analysis, data manipulation, it's kind of almost unlimited, other than obviously computers and power. But all that capability, obviously when you're out in the field, that doesn't do you any real good. Once you have all the data, you can do a lot about a lot of those same capabilities of AI detection, computer vision, any type of analytics, whether you do reporting transforms and things with these new small processors, that run on the edge. You now have a tiny GPU that gets a lot of the same capabilities, not at the just you need to manage the resources, but you can do not only AI but a lot of traditional type analytics as well in real time now. So that's just kind of just to distinguish where everything we do is edge AI. So if you're looking at this, in general, this is anyone that's actually putting some type of robot device, buoy out in the open water. There's some aspect to data. They're not just doing that to have fun. And so while kind of some of this is very related to research, it obviously can be applied and transition into pretty much any type of solution. But as far as the number one thing that we're kind of focused on is getting better data when you're out there. And so that, again, it's a combination of AI, different types of traditional data processing, and then automation. So one of them is maximizing the quality of your data, making sure you get more of the data that you want, that put your assets out there for, and less trivial data. Like you don't need a terabyte of open water data unless you're looking for that's your interest, which is very few people. And then when you do find something of interest, maybe you want a terabyte of data, or you want 30 gigabytes with all your sensors on high resolution. And so that's one of the aspects of better data that we try to achieve. And then the others are creating information real time. That could be obviously AI detection is one type of information. But once you detect something, analyzing that part of the data in different ways to detect, one anomaly and I want to apply some analytics to it in real time, or another anomaly, and on the fly be able to choose what you're processing. The other is just, could be tagging data. So maybe you are collecting constant data as you're going along, but you want to get off when you pull that data. You want to be able to see, jump through interesting points very quickly. And then even that is some of the processing, like point cloud processing and things, where you're doing some stitching. Again, when you're pulling the data off after the mission, you don't want to spend the days processing it. You want to actually have some type of a data product that you can actually start to work on. And then finally, taking some actions. In most of these cases, there's either no operator, but even in a lot of cases, there might be one operator that's running, like say an ROB, but he's currently tasked with also when he finds something, reaching over and starting a data collection on that, or maybe trying to do some maneuver around an object, 360-degree image. And so one of the things about getting that data you want is being able to automate it, whether it's there's someone on the someone there or not at all. Some of that automation would be things like I want to turn on, change the resolution of my camera. So I've been running, at this low resolution or lower resolution while I'm looking for something, but now it's there. Now I want to go to my full resolution, full frame rate. The other could be, sending messages to the vehicle, like, hey, stop for a second and let me collect some data and then continuing to go. Or it's just as simple as, again, just sending a message that, hey, I found something to maybe reduce the comms or something. So the other one is potentially better proposals, and I don't mean this in the sense that it's going to make your the idea of your research necessarily better, but if you've got a lot of competition and your program manager being able to say, hey, we've got AI, we're already working with it, and this is how it's going to help you get your results not only better but faster. You're going to get more for your money. Those kind of things can actually help the proposal. So, just checking that box. So, and obviously there's a lot of other ones, but those are kind of the ones that float to the top and are, I think, probably bring the most value to the table. Okay, so obviously, I think, I guess how many people here are using kind of edge AI right now? Not a lot. How many people here can think that there's possibly something that you thought of where you could use it? Yeah. And hopefully I can change the rest of you guys. So again, the when you see the results, like if anyone saw the demo over there, just that AI running there, it doesn't look very complex. But when you actually sit down to actually try to do this, so you put in your proposal, you say, yeah, we're going to do this, and then you win the proposal, and then your students say, well, how are we going to do that? And then this is what you start to think about. So obviously, you've got to choose a piece of processor, and you've got to install the operating system, and you got to install all the software and things like that. Again, it's not like installing it on a Windows or a desktop. On Linux on a laptop is not compared to trying to install them on some of these embedded processors. And that can take sometimes we'll spend 3 weeks bringing up just the base operating system. And that's with our team that does this all the time. So, okay, you've got that. Now you've got your different sensors, your Pentatils, your INS, GPS. You've got to actually figure out, okay, how am I going to bring that data in? Now you want to process that data, and you need to save that data. And then, and again, along the way, every time you're doing one of these, there's probably at least 100, 1,000 decisions that need to be made. What formats am I saving data in? Things like that. You want to control something usually, whether it's a motor or even hooking up to a control system to do some advanced, again, backseat driver type controls, telling the vehicle, maybe stop or rotate around. And then you've got an AI model. So anybody that's actually trained an AI model, it's actually training an AI model is actually fairly easy if you have the data. Actually really make a great model. It's a little bit harder. But there's also a lot of tools in the cloud. A company called RoboFlow we're talking to, that these companies specialize in helping you create the AI. The problem is when you're done, you press the download button, you get a 300 megabyte file, and you've got to do something with that. And again, that's you need to bring that in. You need to actually load it into GPU memory. You need to get it, start to figure out how you're going to feed it data, take those results and act on them. And then, it's great to get something that all running, but at some point somebody needs to interact with that. And while I've got a display hooked up to that processor running in the back there, in most cases, this equipment is in some watertight housing, and getting actually access to the equipment, to the processor, really hard. So, you need to have a way to interact over a network, Wi-Fi. That doesn't involve using the word Linux or SSH in most cases, because the people working in the field, that's a big step, and it creates a lot of challenges. So, okay. And then I have to say, so we started this project, and I'll show you one of the slides. Projects that really kicked it off. It was a joint project with APL, but this was, 5 years ago, and I had some really great, amazing software people, and another hardware person. I thought, how hard could this be? And it actually turned out to be a lot harder than I thought it was going to be. And one of those challenges is that not only is there, all those different components, but almost every one of those components is a different technology. So you're either working in this language, or you're talking at you're talking to hardware, you're talking to writing JavaScript and things like that, and then you've got everything's embedded, so it adds another layer of complexity. And so not only is the number of things you have to do, but the diversity of the different types. So and so what you end up doing is that means I need more people. And then somehow, even with all those people, it still takes a long time. And so that's it, that really is the challenge that we try to focus on. Is almost all of our customers, a lot of them say, they have engineers that actually can do and probably have done in bits and pieces everything we do. It's again, do you want your engineers spending all their time writing drivers for a sonar, or do you want them integrating your latest, SLAM algorithm or something? Okay, so you've got you put a proposal in, you've got this great idea, you somehow convince the program manager that it's a great idea, and you get the award, and then you start the project, and all of a sudden, after a while, you realize, oh my gosh, I'm wasting all my time on just, putting bits and parts together. And my research is just, the time and money I've left for my actual research is getting smaller and smaller. I need to get in the field. I need to get the data. And so, it actually is a big problem. And obviously one, personally, you want to get to that data analysis. You want to get to that part of your research as fast as possible. That's what you care about. So you wake up every day. But ultimately, obviously, to the customer, the faster you can deliver results and the better those results are, that's where the real value of what you do. Okay, so how do I know? So I'm going to date myself a little bit. I worked with Warren. He worked with me years ago. I'm still young. But this is my a picture from my thesis paper at UT Austin. And so I did a fuzzy logic. I was studying fuzzy logic control systems, and obviously, anybody that wants to get into robots and that kind of stuff, one of the things you have to do is build a robot. And one interesting thing, this was the first digital camera our engineering department had, and you had to go check it out in the morning and check it back in. But what at the end of the thesis, I kind of got where I got some results. I obviously graduated, but I was extremely disappointed because I literally spent, I would say, 70% of my time hooking up all those different sensors, figuring out how to control the motors. I needed to have, even for myself, a user interface so I could see kind of what was happening while it was fun, and as an engineer, I loved it. Very quickly in hindsight, I realized I made a big mistake. And so I didn't know I was going to end up creating this company to solve this problem, but that is the first time I saw it. And then, these are all the other robotic projects that I've actually been involved in. And every time it was the same thing. I don't know if anybody know Doug Warner from the PS. Well, he was while I was working on sonars, they were developing this AUV down there. And I mean, he got a bunch of funding to actually stuff that, it's still a problem today, but obviously optical avoidance, but also detecting impact planning, on the bottom as you're diving down, things like that. And I would say, I worked with him probably for a year and a half on that project, and almost a year and a half of it was just integrating all the onboard processing and the cameras and the sonar. And I think we got 3 runs in a year and a half, and it was towards the very end. And so, and I can go on at each one of these projects, and there's a similar story. And I show these robotic platforms, but again, everything we do, we don't care whether it's on a buoy, we don't care if it's in a factory analyzing something. It's about getting that information and taking some action as fast as possible. So anyway, after all that, this is really what I created the company. That you could put research there or solutions, products, but to change it from you're spending all your time building up the pace to, hey, I can get out in the field in a matter of weeks, and I can start collecting data, and I can actually do more research than I thought I was going to do. So I think some of you guys see in the past where we started with this was developing the software package called NEPI, with the Numurus Edge Platform Interface. And really one of the kind of the vision for it was to, I remember when my PCs only had DOS on it, and I would turn it on and I would get that blinking cursor, and I would write some what was it back then, Fortran, and after a couple of days, I could press a button in the face, I'd have a face or something. But then Windows came along, and it was like, holy crap! I can just, I just plug all this hardware in. I've got applications. I then very quickly after that, I could fix the internet. And it was why are these embedded solutions so hard? When again, over those years, all those projects, it was the same thing. I need to hook a camera up, I need to put a sonar up, I hook my INS up. I need to know where they all are relative to each other. I need to talk to some control system, whether it's a pan tilt. And then I want to actually run some analytics and then make a decision to do something. So the idea is very similar to kind of the Windows concept. Is so you're not plugging keyboards or displays in. You're plugging again cameras, lasers, IMUs, INS, and tilts, and you want that same simplicity that you have with your laptop. So that's one of the goals. The other was data management. So I mean, there's different levels. Obviously, in Python, with a couple lines of code, I can use OpenCV. I can save an image to file. Now, how do I have? But I want to add timestamps to that file name. I want to add location that file name, and then I want it so that I can change on the fly. The frequency that I'm saving that data. I want to be able to switch which data I'm saving at which time. Oh, and I want to actually fuse these point clouds together as I'm going along. Very quickly, you've gone from a few lines of code to again these decisions. How am I going to do that, and then having to get back down it. Let's see. Again, the automation. There is so I was mentioning AI models. So one thing is again, you could say a YOLO layer. There is different model frameworks. Essentially, people have developed to say, okay, this is how I'm going to define a model, the network architecture. This is how I'm going to. Here's the format the information goes in. Here's the format that I spit it out, and here's the whether it's TensorFlow. Or PyTorch or some other application that's actually going to run that. And so again, okay, I've got this model, and now I need to figure out. It's not a matter of just again plugging it into one application. And if you're say a research group, you might end up with a model in this framework, and somebody else brings a model in that framework. And so one thing we do is we manage frameworks. Before the model. So if you're using, say, YOLO 5 models or YOLO 11 models, all you have to do is drop those into the right folder. Our software will detect it in that folder, and it'll load it into GPU memory to correctly get it all processed. And then the automation applications. So, when you see AI running on these small boxes, it's really cool. But then it's like, okay, well, that's a lot of power just to have a box that sits there in your robot and detect stuff. But the value has to come not from the detection itself; it's from the ability to act on that. And so you don't need Word and Excel in these systems. You need applications again for managing your AI models, for connecting. How do I connect cameras to AI models, and how do I automate? So some of that would be a pan and tilt tracking of an object, things like that. And then I mentioned before, again, you don't have keyboards and displays, so it's really a user interface that's as simple as Windows, but is it's through a web browser. And when I say web browser, I'm not talking about a cloud-connected web browser. I'm talking about the software is actually the device itself is running the server. Oh, so there's a quick video, some highlights that kind of just highlight those those different aspects. But one thing that's important that I'll come back to is that what you're going to see is the user interface. But again, these are designed for the most part for autonomous systems. So that the value of that user interface is one, setting it up, maybe monitoring it, post mission accessing data and things like that. But everything you see here, there's API back end. So any data that you see, any button, we're all doing it through our own API, and so it's all it can all be automated, and also through that API, we've got some standard interfaces that I'm talking about. So other systems on the network can actually control this system and obviously get data from it as needed. So the first part again is just showing you some of the user interfaces for setting up your hardware. Once you like where your hardware is at, you can hit save the configuration. Every time you turn it on, that's where it's going to be. Again, quickly choosing different image streams, choosing which AI model. You could have 5 AI models loaded up into memory. You could have 2 of them on this camera, 3 cameras on the other one, and being able to do that with, again, just a few clicks of a mouse or a few commands through the API. Okay, and ultimately getting to different applications. And so the software is really where we spend all our time, but installing that software in the hardware, once again, it's not trivial. And so we sell that in some different hardware packages again, so that our customers can again. Well, I know how much you guys cost per hour based on proposals, so I don't have to tell you if it doesn't take many hours of someone's time to justify a couple $1,000 in a piece of hardware off the shelf. Okay. So I'm going to go through a few different projects that we've worked on or are getting ready to work on. This one, some of you are familiar with it because you may have even worked on it. We were in partnership on the start project with APL, and it was almost my dream project until the program manager of the feature creep. Did anybody run into that? So we had essentially 1,000 low-cost floats out in the water, and they were all connected up through Iridium satellite. Why this program was actually the days this program was going, we and other participants were the biggest users of the Iridium satellite network. But even with that, this was before where we're at now. It was less than 2,000 bytes a day that we could actually move around. But I guess DARPA hard. What they wanted was they had these floats, around there. They wanted to know where their floats were at, and then just on demand, draw a box or a circle or some geofence and say, okay, draw that, click a button, choose. I want this processing. Press a button, and all those floats within an hour are now switched over to that. And then in this area, maybe I'm monitoring some acoustic signal. And this one, we've actually got a hurricane coming in. I want to measure wave heights and wind. And that actually, this took my kind of vision of what could happen, and it pushed it pretty far compared to where things were at when we started the project. But nothing's changed in a sense. We don't do a lot of work through satellites anymore. But the same thing being that, hey, it could be as my vehicle's going around, maybe it's as simple as a geofence, and I'm just switching processing AI sensors as I'm going to different territories or as depths, altitudes, and things like that are changing. So Ocean Arrow, 2 years they came to us, and I don't know if you're familiar with Oceanair. They make a surface autonomous surface vessel that can actually also dive in periods of time. And they spend, I mean, they've got an amazing engineering team. They spend a lot of time, perfecting this platform. But ultimately, their job is to make a platform that you can choose a track, you can choose a location, and it can go out and eventually you can get it back, right? But what what their customers want is they don't, it's pretty expensive just to say, hey, I put this USV up there and it actually didn't do anything, it just drove around for a week. And so when their customers come to them, they obviously have something they want to do. And what we help to do is then, again, be this smart payload where, they integrate our processors and our software into their system. We hook up to all their cameras, their pin and tilt, up to their INS, the vehicle control system. And so that's all sitting there. That's always available, right? And then their customer comes and says, okay, I want to do this with your vehicle. Then either the customer, depending on the tech level, Oceanair, depending on the scope of the work, can do it, or they can come to us and say, okay, we're too busy for this. Can you do this project? But in this case, what they had is this vehicle had 4 cameras, stationary cameras around the vehicle, and a pan and tilt on top of the high-res FLIR camera. And their customer, they wanted to look for ships in a particular area where they deployed the system. And so again, you've got 4 cameras that you can just cycle through. So they were able to, with just 2 clicks, actually set up those 4 cameras cycling at a certain rate. And then if there's a detection, the other thing I did mention that I wanted to say this about the data. So you've got, imagine, you've got your INS, you've got your 4 stationary cameras, you can until camera. All ultimately for an autonomous system and to be scalable, you need to know. You need to not only track, hey, here's here's my INS location, here's a center reference point. I need to know where all of my data is in space at any moment, so that whether I'm stitching it or I'm trying to decide, hey, this detection is here, what direction. And so again, layering on that complexity of data management is something that, again, that's what we our focus is to make that easier. But once they detect on one camera, then they lock, they switch just to that single camera. We can, based on estimated size of the targets, we can obviously do some range bearing estimates. And then we can tell the vehicle to stop, turn that high-res camera over, even switch that to the AI, going into the app. We want to have something moving so that they track it. But ultimately, the customer, all they really wanted is they wanted a high-res picture of the target of interest and a location as quickly as possible. And then so, again, in this case, when we were not doing the satellite communications, but Oceanair, we were just able to tap into theirs and send a picture and location. With that said, this is the same, almost every customer project we're involved in. It's almost the same. I need sensor, I need to hook up these sensors, I need to know where they're at, I need to manage the data, I need to hook up to AI, and I need to take some action. I think we were out in the field with them in 3 months after this project came up, and they had a $10 million order, I think, 3 months after that. So this one was, I don't know if anyone's familiar with Antex, but a lot of the Navy projects I've worked on, right? You get some amazing data. I mean, I've got 3D pictures of mines that I just love to show everyone. But most of that work, and the same thing if you're offshore in the oil industry, most people never get to see that data. So the U.S. Navy puts on Antex down in Port Miami, and they set up essentially an environment where, unfortunately, they don't pay you to come. But if you can make it there and you get your equipment in the water, none of it's classified, or there's no. It's all whatever data you collect there, you can have. And so in this case, what they did is they sunk a bunch of cargo containers. And they put debris fields and things around them. And the idea was just looking at different technologies for how quickly could you, how do you accelerate the disasters? So one of them was, again, you've got these small ROVs, you typically have one operator. And so he's driving around, he's trying not to get his tether caught. But as he's driving, again, what you want is the system itself saying, hey, I detected something, and collect some really high resolution and geotag that, or tell the operator, stop, or and then collect some data. The other is to automate, certain types of data collection. So in this case, what we were automating was the operator could press one of several buttons that would do a 3D. We had a 3D stereo camera in this, and it would, do either a slow transition up and down, or do a rotation. And again, they can press that button, let it do it, and then they have this stitch point cloud that is again ready for an engineering team almost. And then obviously the goal was that data, then we were transmitting that. We had a cell phone connection, and a cell phone data connection modem. And that data was being pumped to a cloud portal and available to engineers anywhere in the world, by the way. But it was actually really cool, having been on a lot of projects, particularly offshore, disaster response and oil rigs fall over and things like that. There is a lot going on. And actually, how many people here have ever funded something offshore to do one of the projects? I know you have. Well, meaning you had to take your money, rent a vessel, and put something out, that you just didn't get to walk down to the dock and drop it over. So just like anybody that's done that knows that when you get it back, if you didn't get any data ops, it's really sad. But if you got a bunch of data and you didn't, but you somehow missed, some of the critical data, it's very painful because it's a lot of money. And then again, this work offshore and things like that, it adds up. The boats we were on, I think it was 150 to 200,000 a day, because not only is the boat, it's the the ROV operators, things like that. This one came up recently. I don't know if anyone's familiar with Sequoia. They're a local company. Jim Decker, I'm sure. Actually, I know he's been here a few times. They do this holographic imaging sensor. So, and Jim can correct me later, but it uses laser through that small window there open to actually essentially they create a data set that you can actually change the focal point after the data collection, and then get so that you can actually find plankton and these small particles in a you can collect I guess an aerial of data in a second, and then you actually have all that data in there. The problem that I guess a lot of their customers find is, one is that, like many offshore operations, they just turn on the data collection, they send it out. And two, the actual process of analyzing the data is very manual, because it involves not only the time stepping through, but now in each time slice, I need to step through the range. And so what we're working with them at is one is as the system is running, we can't process all of their data in real time. It's actually too process intensive. But what we can do is we can process a chunk of water pretty in depth, say every second, and analyze, just one, tag that chunk, that volume of water with detections, other metadata, the location, depth, and things like that. But we can also, through that one point, we have statistics of this type of plankton, this many percentage of this type of plankton versus that, and so we can start creating those statistics that are, they've got this metadata associated with it, and then taking all that information, then you can actually put this is all valuable. So when I pull that data, I've got all these tags, and I know, hey, and I can actually create a map, and I can see biodensity or something like that in different areas. And but ultimately, what they really don't want to do is they don't want to come back with giant collections of data that there's actually no particles or plankton or whatever they're looking for in it. And so to take that information while we're creating real time and then to make decisions. So again, adjusting the sensor. I haven't used it, but I'm guessing there's probably a few knobs up there that if you could adjust in real time would make a big difference. Obviously saving the data. Georeferencing. So, again, if you're sending this out, maybe it's a day, depending on what the platform is, but maybe it's a day to get to the actual, the island, around the island, or the reef, or whatever you're working on. You don't want to collect all that data. And so geofencing is obviously one way to deal with that. This is another project that we just got awarded, and it's improving on laser line. So for those that don't know, you can take an image and you can put a very bright laser line in that image, and knowing where your camera is that is looking at that image, where your laser is, you can triangulate. If you know the pixel of where that laser is hitting, you can actually pull out a three-dimensional line, and then as you're moving along, you can stitch that, and you can create extremely high resolution data. Which this is a mooring chain for an offshore oil rig. That right now, the way that they inspect it, they have to actually pull up those mooring chains onto deck or onto some a platform that's actually comes in, is designed to do that, and they physically manually inspect that. And so the laser is great, except that it's a lot of data, and where you have a perfect line hitting a perfect, almost flat but surface with the right texture, it's pretty easy to pick out that pixel. But what they find is that same processing falls apart in a lot of cases, and one being when you're going around these corners and things like that. And so while there's different processing you could do, to adapt that, one is what you don't want to do. These are very high resolution pictures, and so you don't want to apply, say, 5 different analytic techniques to every picture, because you actually, a lot of those are almost pixel by pixel, okay, groups of pixels. And then even if you do that, how do you fuse those together? How do you know which is the best analytics for which? So in this project, what we will be doing is the customers actually, they're experts in essentially collecting this data, but drawing these lines. I should say they know what they're looking at, and that's a better way of putting it. And so what they give us is they're giving us like 500 pictures of both easy and really hard places, and they're growing in and they're drawing boxes around particular hard areas. And so what we'll do with that is then we'll have our own people do the same thing with say like 5,000 pictures. And then each one of those different boxes may have we'll give it a tag. So one will be flat, one will be curved, one might be intensity spread, right? Like so the surface, the angle, it's spreading. And then our team will create those boxes, we'll create an AI, and then what we'll do then is it'll be able to find those spots, but then we'll apply those particular types of analytics to each one of those boxes as we go. Which one, obviously, if we do, if I'm taking maybe less than 5%, area and applying a very computationally heavy process, I can do that. And I can do it in real time. And then because I've actually segmented this, I can actually much easier to start fusion because they are somewhat already broken up, and really all I'm doing is not trying to decide what to fuse in one place, but how do I just make that together. And then the third is one of the boxes is going to be where like a fish has come through and blocked the line. And then for that one, we're actually going to try to train an AI to actually draw that line. So, I mean, and the way to do that is someone will make a decision and say, this is what these lines should look like. With enough of that, the AI should be able to make that same decision. Okay. Are we doing time? It's 11 minutes. Really? Okay, yeah. Perfect. Okay, just all I want to talk about now is okay, so hopefully I've shown you some ideas that maybe might be interesting. And what I want to do is show you how easy it is to actually do this stuff. So one is, like I said, you can get our software, but unless you really love playing around with Linux and embedded systems, most of our customers just say, just buy some of your box with the software installed. And so we have, just this kind of, hey, take our electronic stack and you put it in your own. You've got your housing already, or different environmental housings. I know what happened to you, maybe 95 of you is thinking, well, that's a lot of power. As soon as you work NVIDIA or GPU. And so while most of our customers, they want more power in these smaller boxes. We also have projects where you can use a Raspberry Pi, and you're not getting 10 frames a second in the AI detection. But in most of those cases, if they have to wait, say 1 or 2 seconds for an AI to analyze something, then analyze another, they can still achieve their goals and at a much lower power level. The other is also for that the smart float project. What we did is we had an analog to digital triggering system that would actually it was just looking for like levels on the hydrophones and things like that, and it would turn on the system. And so it was a very small microcontroller that was running in its sleep mode most of the time. So we get connect all your hardware. If you're walking out, or if you saw it coming in, all of that equipment over there is it's just a fraction of all the equipment we test with whenever we release a new version of software. That's all supported, and that's all comes from our partners that have either given or loaned us that equipment because they also see the value in this. And one thing you do get again with us is we're continuously adding new hardware capabilities that again and our customers, all of our customers are available to access it. Bring in your analytics, your AI, and then for your the applications. And so what we have actually, the easiest way to kind of automate something is we've got an automation script manager where you just drop your Python files into this folder. You can, and then we have, like I said, an API that really at the top level, it's very high level. It's just a few lines of code. People that have never heard before can create some amazing analytics. Automation. But we also go all the way down to at the very bottom. There's ROS 2, and so you can actually everything's controllable and all the data is available to do that. But a typical project would be starting off with, again, writing this Python automation script that essentially does everything I want, but it's really more of a prototype for the research and testing phase. And then, I've got it. I really like how this is working. And then we have a system that manages applications that has a user interface. And so you can take that and within a matter of days, create an actual full user interface, deploy it as an application that then is available in the system. And what's cool about that too is that we have customers that create their applications based on their research or development, and then we market it to our other customers. And so say, hey, these guys, they created this, and now we're a channel for their research or the output of the research. In a lot of cases, it's not monetized, but in some cases it is, where they have a way to actually make money off of research. And then, well, I touched on this already, but that was really kind of the user setup. And then there's the customization. But again, all of our stuff is either open source or even the stuff that's not fully open source, it's code available. And so you can take that and quickly modify it. I always tell people, if you give me something that works and versus a white piece of paper, I can usually hack something together really quickly with something that works, modifying it. But, if you start building stuff from scratch, and so it's amazing to me how having an example that's close to what you want can get you all the way through. And then again, on the user interface side, that's all customizable. It's all React JS with, again, a bunch of libraries in there for buttons and things like that. And just like the drivers, we are continuously, every project, we'll add another application available, and our system manages applications. So when you turn it on, not all this stuff is running. There's an application drop down that says you can turn off and on applications as needed. Just like the same thing with the driver and your AI. We ultimately want to empower our customers, and so there's a lot of we really don't hide anything. We spend a lot of time on documentation and videos to actually, anything we do in-house, ultimately we want our customers and our partners to be able to do themselves. And so one of the points here is for anyone that's ever kind of developed something, not necessarily from scratch, but goes out, here's an open source package over here, one over here, and they get it, and something doesn't work. A lot of times you'll spend a day, if not 2 days, just searching the internet forums for one other person that may have ran into that. With our stuff, you can actually, if you've got a support service, you can get on the line or give us a call, and you're talking to the person that write the code and get that solved in a matter of minutes usually. All right, so just kind of wrapping up again, what we're focused on is selling these smart data hardware and software solution products. But almost all the projects we're involved in, at some level, we're supporting the customer. They want to leverage our expertise to accelerate their project as well. And in some cases, we'll actually prototype. I think there's a flash somewhere, a case study somewhere. Westmart, we actually prototyped their next generation sonar processor, which brought in their sonar and cameras and turned what, actually the player with the scanning sonar, if you crawled in sonar systems, what we added was we brought their GPS information in, and we're able to estimate where the net was relative to GPS. And so we were able to very quickly start making 3D visualizations where they were actually measuring 3D biomass, and then hooking their camera up that's in the net and doing estimates of biocatch and things like that. Okay, so all right, guys, thanks everybody. Any questions?
Could you address you mentioned open source. Could you address any of the proprietary differences, or is there IEEE standards you're using, or are we knocking our heads against?
Well, actually, what was the question though, particularly?
Well, you mentioned your.
Oh, okay. Yeah, so I guess so open source, obviously there's just like it has its own politics. There's different extremes that different people believe, what it should be. But ultimately, if you say open source, what you mean is that you really can take this and you can do whatever you want with it. And you never have to come back to us. And then there's some layers that make it a little bit hard. It says, okay, but you can take it. If you change it, you got to put it back out in the world. And so what we've done is, so for the 90% of our NEPI software is completely open source, and BSD3, which is really, I guess, non-permissive license, and it lets you do a lot, I guess. But what that software does is it manages three things. It manages the drivers. It manages the AI frameworks. So again, there's maybe 10 different frameworks and models you have, and somebody's got to write that interface layer for each one of them that bring it into the system, make it. And then there's the applications like pan and tilt tracking. We're working on a pan and tilt INS stabilizer so that different USBs, as there's some wave motion, they're able to lock on and keep their targets. So that's we license those in the sense that they're not open source. The code's available. You can take them, but you can't use them commercially unless you bought either a system that has a licensed software, or you've gotten our software and you've licensed that. And we don't do subscription licensing and things like that. It's just like, actually, I don't even, maybe that's changed probably even for Windows, but back in the day, you would buy a piece of software, there's Adobe, and it was yours. And, the only time they would give you a hard time is when, you start trying to put it on a bunch of other machines. And so that's really our thing is, one, once you get it, you don't ever have to come back to us. Two, being that because 90% of it is open source, you're not adopting a proprietary platform to build on. You are just paying what you're paying for with us is again more acceleration. That hey, you could write that driver interface, or I'm just going to license your library driver interface. But ultimately, we do have to make money, and so and actually those drivers, they can take anywhere from a couple of days to a couple of weeks, depending on the complexity of the manufacturer's interface, things like that. And so there's a lot of value in them, but it also costs us. We've got a full-time person, and that's all they do is write drivers. Did that answer your question?
Good.
Anybody else?
Yeah, so when I hear edge AI, I think learning on the fly. Is that really what's happening here?
No, not at all. No, this is just applying learned, trained models all the time. But I say that's just really another layer of capability, real time, learning, unsupervised learning while you're going. But that, I think, one, is probably more researchy than, there's not a lot available out there to actually do that. Two, if you're, the actual learning is actually much higher intensity of resources than the processing. And so, you now maybe not doubled, you may have tripled your power if you're trying to do, learning while you're actually doing inference and things like that. But with that said, I think that is the future, is that these things should be able to learn and fly. If you have cloud connectivity, obviously there's a lot of resources there that could actually be updating a model in real time on the edge. Because there's
You talked about the ROS. A lot of this sounds like ROS middleware.
Yeah, well, I mean,
I'm curious
so
what
we
you-
built everything on ROS. So I mean, ROS is it's fundamentally a communications, publish subscribe communication system with a between different nodes or different processes running. And what ROS has done really well is they've said, okay, here's a list of standards. So if you're creating an image, you're going to use this message so that anybody else, not only in your office but in the world, that writes a component that says, I want to take an image in, they know how to ask for it, that. And then there are different people or organizations that have written, those little notes, little processes that do more. And so what we've done is, okay, we built kind of on top of that to say, okay, here's a library of not only nodes, but here's a library of nodes that actually connect to the real world, connect to hardware, and things like that. Here's a set of nodes that connect to AI and manage AI. Here's a web-based user interface that talks to connects to this ROS node and provides that. And so we've just and we've used ROS as our communications and interface tool. But what you don't do with ROS is kind of all these capabilities wrapped up and ready to go. Does that make sense? All right. Well, thanks again, everyone.